The fourth section of this chapter is about acceleration. So just as velocity is the rate of change of displacement with time, acceleration is the rate of change of velocity with time. Because of that, an object accelerates whenever its velocity changes, no matter what the change is. So it accelerates when its velocity is increasing or its velocity is decreasing. We will begin with the definition of average acceleration, which is the change in velocity divided by the change in time. Here the change in velocity is v final minus v initial, and change in time is t final minus t initial. AV means the average acceleration. Now the SI unit of average acceleration is meters per second over second. Acceleration is velocity over time, so the units is units of velocity, that means meters per second, over units of time, that means seconds. So the SI unit of average acceleration is meters per second square or ms minus 2. An average acceleration can be positive or negative or zero depending on the direction. Again, acceleration has both magnitude and a direction like velocity. Because of that, it's a vector quantity. Let's see an example of calculating average acceleration. So we have the equation for average acceleration. We just learned the equation. Suppose a car can go from 0 to 60 miles per hour in 7.4 seconds. Now what is the average acceleration of this car in meters per second squared? And we have given 1 mile is equal to 1609 meters. Now the equation for the average acceleration is AV equals delta V over delta T, or V final minus V initial over T final minus T initial. So we can substitute the numerical values to this equation to get the average acceleration. So AV is equal to V final means 60 miles per hour. So this should be 60.0 miles per hour minus initial velocity is 0 and the time is 7.40 seconds minus 0. So the answer is 60 over 7.4, and now we have to convert these miles and hours to meters and seconds. So 60 miles per hour means over 1 hour, and this we have to convert it into meters, and we got that 1 mile is equal to 1609 meters. So because of that, we have to multiply by 1609 meters, which is equal to 1 mile. So we wrote it down such a way that the miles get cancelled. And now we have another term, 1 over 7.40 seconds. Now we have to convert it into, we have to convert this hour into seconds. So we have to multiply by 1 hour over 1 hour is equal to 3600 seconds. Now the units of miles cancels and hour cancels. So we are getting the answers in meter per second square. So the answer is 3.62 meters per second squared, or ms minus 2. So let's quickly look at another example. An airplane has an average acceleration of 2.19 meters per second squared during the takeoff. If the plane starts at rest, how much time does it take for it to reach a speed of 174 miles per hour? Now again we have the same equation of average acceleration, which is delta v over delta t. Now we have to find the time it takes to reach the speed of 174. So the final velocity is 174. So to find the delta t, we can isolate delta t from this equation. So delta t is equal to delta v. We can take the delta t here and then divide the whole equation by av, and then we will get delta t is equal to delta v over av. Now what is the change in velocity? So it starts from 0 and goes to 174 miles per hour. So it is 174 miles per hour minus 0 means just the 174. And the average acceleration is given 2.19 meters per second squared. Now we have to calculate the time, but in here for delta v, time is in hours, and for acceleration time is in seconds. So we have to convert it into 1 units. Let's convert it into the standard unit of seconds. And again 174 miles. We have to convert this. This is 174 miles per hour. And now let's convert it into meters first. 1609 meter is equal to 1 mile. And then we have the acceleration value 2.19 meters per second squared, and then we need to convert this 1 hour to seconds, 3600 seconds. Now the miles get cancelled, hours get cancelled, and this meter get cancelled. This has 1 second and this is s minus 2, so 1 s is get cancelled. So the answer is 35.5 seconds. So the final unit is in seconds. Now let's see what's the instantaneous acceleration. So we learned about the instantaneous velocity, and similarly we consider the limit of smaller and smaller time intervals to find an instantaneous velocity, to find the instantaneous acceleration similar to the instantaneous velocity. So therefore the instantaneous acceleration is the acceleration corresponding to an instant of time. A equals to limit delta t goes to 0 delta v over delta t. So again here delta t goes to 0 means evaluating the acceleration over smaller and smaller time intervals approaching 0 in the limit. As you might expect, instant acceleration is a vector just like the average acceleration, and its direction in one dimension is given by its sign. Again the SI units of instant acceleration is meters per second squared, similar to the average acceleration units. So one final note before we go to some examples. If the acceleration is constant, the instantaneous and average accelerations are same. To see how acceleration can be interpreted graphically, suppose a particle has a constant acceleration of 0.50 meters per second squared. That means that the velocity of the particle decreases by 0.50 meters per second each second. So if its velocity is 1 meters per second at t equals 0, then at t equals 1, its velocity is 0.05 meters per second. And The next, at t equals 2, its velocity becomes 0, and then at t equals 3, again its velocity is minus 0.5 meters per second, and so on. This is minus 0.5 meters per second. So this is illustrated in this curve. So this is v versus plot curve. We have a straight line with a negative slope because the constant acceleration is minus 0.50. The slope is negative. And this curve 2, there's another curve represented in here. It has a positive slope corresponding to a constant acceleration of 0.25 meters per second. So in the velocity versus t plot or v versus t plot, constant acceleration gives a straight line graph and the slope of the graph gives the acceleration. Now let's see the graphical representation of average and instantaneous acceleration. So graphical representation of velocity means the x versus t graph or position versus time graph, whereas the graphical representation of acceleration is the velocity versus time graph or v versus t graph. So in the v versus t plot, average acceleration corresponds to the slope of the straight line segments connecting different points. This is very similar to the instantaneous velocity and average velocity. So as we told earlier, in the x versus t plot, instant velocity is the slope of the tangent line. So similarly, instant acceleration is given by the slope of the tangent line at the time t3 in this case. And the average acceleration is given by the slope of this line segment between the two corresponding times. So this representation is very similar to the representation of average velocity. Instead we have v versus t graph. In average velocity graph we have x versus t plot. Let's see one more example on acceleration. So a cyclist riding in a straight line has an initial velocity of 3.5 meters per second. So the initial velocity is given and he accelerates at minus 1.0 meters per second squared for 2 seconds. So within the first 2 seconds its acceleration has a minus value, negative value. So it should be decreasing. Now the cyclist then coasts with 0 acceleration for 3 seconds. That means acceleration is 0 for the next 3 seconds. And finally he accelerates at 1.5 meters per second square for an additional 2 seconds. That means at the final 2 seconds his acceleration is a positive value. So now we have asked to find the final velocity of the cyclist and also the average acceleration of the cyclist for these 7 seconds. So he rode the bicycle for 7 seconds. Now first of all, let's sketch a velocity versus time plot for this cyclist. Then it will be very easy to visualize the problem. Now in here, for the first 2 seconds, the cyclist has a negative acceleration of minus 1, and for the next 3 seconds he has a 0 acceleration. In that case the velocity is constant. Acceleration is 0 means there is no change in velocity. Because of that we have a constant velocity at that time. And then at the final 2 seconds he is accelerating at 1.5 meters per second squared. So it's a positive value. Because of that it is increasing. The velocity is increasing. So each interval of constant acceleration is represented by a straight line of the appropriate slope. So the line connecting the initial and final points should determine the average acceleration. Now we list the parameters given in the problems. The known parameters, we have given the initial velocity, which is 3.5 meters per second, and a1 is the acceleration. In first 2 seconds it is -1, and after acceleration in the next 3 seconds a2 is 0, and the acceleration is in final 2 seconds, which is a3, is 1.5 meters per second. Now what are the unknowns? We are asked to find the final velocity and the average accelerations. So we know two equations. We know acceleration is delta v over delta t, and we know delta v, the change in velocity, is v final minus v initial. So first let's find the final velocity, which is Vf. So we know that delta V is equal to V final minus V initial. Delta V is equal to V final minus V initial. And now we need to find V final. So we can isolate V final. It is equal to delta V plus V initial. Now V initial is given, which is 3.5 meters per second. V initial is given, which is equal to 3.5 meters per second. So to find the final velocity, we need to find the delta V. Now what is delta V? Change in velocity. So we have 3 different line segments with 3 different acceleration values. So delta V is delta V1 plus delta V2 plus delta V3. That means change in velocity at the first line segment, which is delta V1, and change in velocity in the second line segment, which is delta V2, and the change in velocity in the third line segment, which is delta V3. Okay, so I will write delta V is equal to delta V1, then delta V2 plus delta V3. Now first let's find the delta V1, and from this equation we can find delta V if we know the acceleration. So del A is equal to delta V over delta t, and we can find delta V by multiplying acceleration by delta t. So for each time interval we know the time interval and acceleration values. So we can find each delta V separately. So for the first segment, acceleration is -1 and delta t is 2 seconds. So this is -1 meters per second squared times 2.0 seconds, and it gives -2.0 meters per second. Now delta V2 is again acceleration times the time at that time interval. So in the second segment, acceleration is 0 times delta t2. Because of that, the answer is 0. There is no change in velocity because the velocity is constant in the second segment. And in the third segment, delta v3 is again a3 times delta t3. a3 is given 1.5 meters per second squared. Time is again 2 seconds. So the answer is 3.0 meters per second. Now we can find delta V. which is equal to delta V1 plus delta V2 plus delta V3. So the answer is minus 2.0 meters per second. Delta V2 is 0. Delta V3 is 3.0 meters per second. So the answer is 1.0 meters per second. Now we know delta V and we know V initial, which is given, so we can find the final velocity. So the final velocity is delta V plus P initial. Delta V, we just found the value 1.0 meters per second, and Vi is given in here, it is 3.5 meters per second. So the answer is 4.5 meters per second. Now we can find the average acceleration AV. So AV is delta V over delta T. Now what is delta V? We just found the value of delta V, which is 1.0 meters per second. And what is the total delta T? And we know that the cyclist accelerate up to 7 seconds. So the delta is 7 seconds minus 0, that means 7. So it is 7.0 second. So the answer is 0.14 meters per second squared. So likewise you can find the average acceleration or average velocity from these type of graphs. So in one dimension, velocities and accelerations are either positive or negative, depending on whether they point in the positive or negative direction of the coordinate system chosen. So when the velocity and acceleration of an object have the same sign, that means they are both pointing in the same direction. Like in the figure A and B, acceleration and velocity are pointing in the same direction. Here also acceleration and velocity are pointing in the same direction. Then the speed of the object increases. The speed is increasing. So it is accelerating. And when the velocity and acceleration of the object have opposite signs, like in figure B and D, the speed of the object decreases. Figure B and C. So the acceleration is in negative x direction, velocity is in positive x direction. So the speed is decreasing. In here also, acceleration is in the positive x direction, velocity is in the negative x direction. Because of that, the speed is decreasing. So when the particle's speed decreases, it is often said to be deaccelerating. But this is not a negative acceleration, it is simply the deacceleration. So deacceleration can cause by a positive or negative acceleration, depending on the direction of the initial velocity. For example, in part B, acceleration and velocity are in two opposite directions. Because of that, it is deaccelerating. But it is deaccelerating in negative x direction because A is pointing in the negative x direction. But in figure C, again acceleration and velocity have two different directions. So it is deaccelerating, but the acceleration is pointing towards the positive x direction. Because of that, it has a positive value. So that concludes the fourth section of our chapter 2.